Well, hello geometers and general seekers of truth. Welcome to the video on finding areas of regular polygons. And in this video, we will start with a regular pentagon. Now, just to refresh your memory a little bit, a regular pentagon is a pentagon with all equal sides and equal angles. So let me try to draw this as best I can. This is by no means perfect. So a regular pentagon approximately looks something like this. And again, these side lengths here are supposed to be congruent, so these are all congruent side lengths. It has a radius of 8, and now keep in mind the radius is the length from the center of the pentagon, of the regular pentagon, to one of the vertices. So this length here is 8. Okay? And in fact, all of these radii are 8 because by virtue of being a radius, that's what it means. So we have the shape here with these red line segments here, they're all 8. Okay? So they're all equal to each other, they're all equal to 8. And our goal now is to try and figure out what is the area of this shape. Well, let's approach it in a very systematic way. Notice here that the pentagon is equal to the area of these 5 triangles, but the 5 triangles are all the same size. So we really just need to do is figure out the area of one triangle. So we're going to find the area, excuse me here, my pen's not working. Let's find the area of just one triangle. All right, so effectively, we want the area of this object here. This has a side length of 8, this has a side length of 8, and it may seem that this problem is unsolvable, but rest assured it is possible to solve, because remember that the central angle, in other words this angle right here, is equal to 360 divided by the number of sides. Okay, there's 5 triangles, they all add up, 5 angles I should say, they all add up to 360. They're each equal to each other. So that means each one of them has to equal 360 divided by 5, or 72 degrees. So we have here, this angle is 72 degrees. Please pardon the messiness here. My pen's not working too well. But maybe we can break this problem out even further. What if we cut that triangle in half? And now we just look at the area of one of these smaller triangles. So let's just investigate and look into that and see what that looks like. Well, we have a length here. See, you have, one length. Try it again. You have a length right down the middle here. You have another length here. This is the radius, which is the hypotenuse of the triangle, and you have this length there. So let's see, putting it all together, we know that now this length here is 8. Now this little angle is 1/2 of 72, or 36 degrees. So from this, we can figure out, from this little bit of information, we can figure out the area of the entire pentagon. So if you notice that the pentagon now is 10 times the size of one of these triangles. This blue right triangle, there's 10 of them in the pentagon. So we can find the area of one of these right triangles, we can find the area of the entire pentagon. And to do that, we need to find the height and the base. So I'll label, maybe I should label this B instead of X. Okay, so the base here is B. And the height is H. Well, to figure out these values, let's use our knowledge of trigonometry. So let's see, I'll write it on the side down here. To find H, we're going to use the cosine ratio because this length here is adjacent to the 36 degree angle. So the cosine of 36 degrees is equal to H over 8. So that means 8 cosine of 36 is equal to H. Now, whatever this number is, I'm not going to worry too much about it at the moment. I'll just circle it, knowing that this is an important piece of information. And now let's look at the base. Well, this base down here is the opposite side of 36 degrees, so we will use the sine ratio. The sine of 36 degrees is equal to b, the base, over 8. So that means 8 times the sine of 36 is equal to b. And once again, whatever is this value, I'm not going to worry too much about it. We'll put it all together into the final step here. But we know that this is how we calculate b, the base. All right, so now let's look at the area of one of these triangles. Well, the area is 1/2 the base, which is 8 sine of 36 times the height, which is 8 times the cosine of 36. Times the cosine of 36 degrees. Okay. So that's the area of one of these triangles. Well, what about the area of the entire pentagon? Well, remember that the pentagon is 10 times the size of one of these right triangles. So all we have to do is multiply this entire expression by 10. So let me write up here. So let's go back to the original problem. The area of the pentagon is 10 times the pentagon is 10 times the area of this triangle here. So this is equal to 10 multiplied by 1/2, 8 sine of 36 degrees. This pen is terrible. Let's try that again. 36 degrees times 8 cosine of 36 degrees. And I'm going to simplify this a little bit further as follows. I have 10 and 1/2, so that's just going to give me 5. I have 8 and 8, so that's going to give me 8 squared. And then finally, once again, sine of 36 and cosine of 36. Sine of 36 degrees and cosine of 36 degrees. And this all comes out to approximately 152.029 units squared. So this is my final answer for the area of a regular pentagon. And I want to emphasize a few key things here that we did. We took this problem and we approached it by breaking it down into a bunch of triangles. And then we broke each of those ones down into a bunch of smaller triangles. And then used trigonometry to solve for the length and the base of the height. And then multiply by the number of triangles. Now, I want to look at this equation here, this expression here, that we use to get our final answer. So think, where does 5 come from? Is it always going to be 5? What if this was an octagon? What would this number be? Why 8 squared? Okay, where did the 8 come from? And then where did 36 come from? Okay, so this is important pieces of information. And if you want to be a serious math student, you want to develop a better understanding for mathematics, we have to think beyond the problem. We have to think what else does this apply to? If I change this question a little bit, if I have a 20-sided shape, which of these numbers will really change and how will they change? So I'll leave you on that note for a little bit of further thinking as we will progress forward into some more difficult examples. As always, ask for help if you need it. Thank you for watching and have a wonderful